This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on the first derivative test. Initially, we're going to examine the notion of critical values. What are they? Well, they occur at points x where the first derivative is 0 or where the first derivative does not exist. If the first derivative is 0, the tangent line is horizontal, and that gives us a possibility of having a minimum or a maximum. If the first derivative doesn't exist, if the function is continuous, it may be a sharp corner, which also gives us an opportunity to possibly have a minimum or a maximum. So we're going to look for critical values first. The way we're going to do that, we're going to look at the first derivative and set it equal to 0 or find values where that first derivative does not exist. So for this example, let's take a look at f of x is x cubed plus 3x squared minus 9x plus 5. If we want critical values, we've got to find the first derivative, and f prime of x is 3x squared plus 6x minus 9. Set it equal to 0 or find out where it does not exist. So setting it equal to 0, we get 3x squared plus 6x minus 9. It always exists. The domain of the derivative function is all real numbers. So there will be no case where the first derivative doesn't exist. But we can find values where the first derivative is 0. Factoring out a 3, we get 0 is 3 times x squared plus 2x minus 3. Factoring that trinomial, we get 0 is 3 times x plus 3 times x minus 1. So setting x plus 3 and x minus 1 equal to 0, we get x is negative 3 or x is 1. So those are the critical values for this function. Critical values, places where the first derivative is 0, which happened in this case, or where the first derivative does not exist. Let's look at another function. F of x is 4 plus the cube root of x minus 5 squared. We need to take a derivative, but let's rewrite this first as f of x is 4 plus x minus 5 to the 2/3 power. Taking the derivative of 4 is 0, but the derivative of x minus 5 to the 2/3 is 2/3 x minus 5 to the 2/3 minus 1, or 2/3 x minus 5 to the negative 1/3. Let's rewrite this as 2 over 3 times x minus 5 to the 1/3 power. And the 1/3 power is just the cube root. And then we can ask ourselves, when does this equal 0? And the answer is never. For a fraction to equal 0, the numerator has to equal 0, and the numerator is always 2. So this fraction is never 0, but it does not exist when x is 5. Because when x is 5, we are dividing by 0, which is not possible. So f prime of 5 does not exist. The derivative does not exist at 5, therefore 5 is a critical value. So in these two functions, we've identified all of the critical values, but the next step is to determine whether a critical value is a minimum, a maximum, or neither. When I say minimum, I mean relative minimum or local minimum, i.e. the smallest in your neighborhood. Same thing with a maximum, a local max, a relative max, the largest number in a given neighborhood. So here's our first derivative test. If a function is increasing to the left of a critical value and decreasing to the right, then we have to achieve a local maximum at that critical value, highest number in the neighborhood. Here's a way to think about this. If our critical value is c, it's increasing to the left and decreasing to the right, then c will be a maximum. The other case, if it's decreasing to the left and then increasing to the right, we're going to get a local minimum, smallest number in the neighborhood, which we can see this way. Decreasing to the left of c, increasing to the right of c. The value at c, the y value, the function value at c, should be the lowest in the neighborhood. So let's revisit those first two functions we looked at. So we looked at f of x is x cubed plus 3x squared minus 9x plus 5. Quick review, set the derivative equal to 0, factor it, and we have critical values of negative 3 or 1. And we need to see what happens on either side of those critical values. So here's the function, here's the derivative. Critical values are negative 3 and 1. Choose a number in each interval. Choose a number to the left of negative 3. Choose a number between negative 3 and 1. Choose a number to the right of 1. And then we will determine whether the function is increasing or decreasing on those intervals. I've chosen negative 4 to be left of negative 3. I've chosen 0 to be between negative 3 and 1. And when you can choose 0, choose 0. The algebra is easy. Something beyond 1, I just chose 2. So the next thing I'm going to do is I'm going to look at the derivative at -4. So is the function increasing at -4 or is the function decreasing at -4? So we'll plug -4 into the derivative function. So f prime of -4, 3 times -4 plus 6 times -4 minus 9. 48 minus 24 minus 9. What's that going to give me? 48 minus 24 is 24 minus 9 is 15. But it's positive 15. So at -4, the function is increasing. It is going up. So let's draw an arrow that shows that. At -4, the function is increasing. The derivative is positive. The function is increasing. Next up, we're going to plug 0 into the derivative function. 3 times 0 squared plus 6 times 0 minus 9. That you can probably do in your head. 0 plus 0 minus 9. We get f prime of 0 is -9. So in this interval, the function is decreasing. Well, if it's increasing to the left of -3 and decreasing to the right of -3, we know we will have a local max at -3. But I'm not finished. I also need to see what's happening at 2. Let's plug 2 into the derivative function. 3 times 2 squared plus 6 times 2 minus 9. 12 plus 12, 24. 24 minus 9, positive 15. So it's increasing here, increasing to the right of 1. So what does that tell us? We're going to have a local min at 1, decreasing to the left, increasing to the right. Again, local max at x equals 3, local min at x equals 1. And -3 and 1 were critical values because the derivative at those numbers was 0. We had a horizontal tangent line, which you can see here. -3 horizontal tangent line, slope is 0. Increasing to the left, decreasing to the right, local max at x equals -3. Horizontal tangent line at 1, decreasing to the left, increasing to the right, local minimum at 1. Now the other function we looked at was this one. F of x is 4 plus the cube root of x minus 5 squared. We rewrote the function this way, took its derivative, and looked for critical values, but there was never a point where the first derivative is 0, but we said f prime of 5 did not exist. So 5 is a critical value, and then we'll check the derivative on either side of 5 to see if 5 is a minimum or a maximum or neither. So I chose 4 on the left, I chose 6 on the right. 5 is a critical value because f prime of 5 does not exist. I need to look at f prime of 4, plug in 4 for x. 4 minus 5 is -1. Cube root of -1, also -1. So I get 2 over 3 times -1, or -2/3. So at 4, the function is decreasing. And we draw that arrow in. Now choosing a number to the right of 5, I chose 6. That makes the arithmetic fairly easy. F prime of 6, plugging in 6 for x. 6 minus 5 is 1. Cube root of 1 is 1. 3 times 1 is 3. And you see how this is going to go. And we have f prime of 6 is positive 2/3. So that will be increasing there. Well, if the function is decreasing to the left of the critical value and increasing to the right, we must have a local min at the critical value of 5. Local min at x equals 5. Let's take a look at one more of these, or look at our graph first. So here is that function. It's decreasing to the left, sharp corner here, increasing to the right. We can't really talk about a tangent line because the derivative doesn't exist there, but indeed, at x equals 5, that is a local min, that is the lowest y value in the neighborhood. In fact, it's the lowest y value anywhere, but it certainly is a local min as well at x equals 5. Let's take a look at one more function. F of x is x to the 4th plus x cubed minus 3x squared minus 5x minus 2. We need to find the critical values, so we're going to take the first derivative and set it equal to 0. First derivative, 4x cubed plus 3x squared minus 6x minus 5. Set it equal to 0. And that's kind of a challenging problem. Many ways you can do this. You could guess some numbers. You could use synthetic division to reduce it. You could use a graphing calculator to find out the roots. I'm going to factor it. It just so happens that it's x plus 1 times x plus 1 times 4x minus 5. If that's the case, then x would equal -1, or 4x minus 5 is 0, x is 5/4, would be our critical values. Those are the values where the first derivative is 0. There are no values where the first derivative does not exist. So I have the function, we have the derivative, we have the critical values at -1 and at 5/4. We've got to choose numbers in each interval. To the left of -1, I chose -2. Between -1 and 5/4, I chose 0. Beyond 5/4, which is 1 1/4, I chose 2. I want the derivative at -2, the derivative at 0, the derivative at 2. So we're going to first plug -2 into this function and see what we get. F prime of -2, 4 times -2 cubed, 3 times -2 squared, minus 6 times -2 minus 5. -8 times 4, -32. 3 times 4 is 12, minus 12 minus 5. What is that going to give us? 32 plus 12 minus 5, which is -13. So at -2, the derivative is negative, so the function is decreasing. We draw that arrow. Next up, we're going to plug in 0. But if you plug in 0, what do you get? 4 times 0 cubed, 0. 3 times 0 squared, 0. Minus 6 times 0, 0 minus 5. I get -5. Also decreasing. So f prime of 0 is -5. The function is also decreasing. So what happens at this critical value? Is -1 a minimum or a maximum? Well, it's neither. It's decreasing. It has a horizontal slope, and then it keeps decreasing. If that happens, -1 is neither a minimum nor a maximum. Finally, we're going to plug 2 in. So 2 cubed, 8 times 4 is 32. 2 squared is 4 times 3 is 12. Minus 6 times 2 minus 12 minus 5. That's a positive number. We get a total of positive 27. So therefore, if it's positive, the arrow is going up. And in that situation, we can conclude that we have a local minimum at 5/4. Goes down, then goes up. Local min at 5/4. What does that graph of that function actually look like? It's decreasing, then it flattens out at -1, and it continues to decrease. So -1 has a horizontal tangent, but it is neither a local min nor a local max. But when I get to 5/4, 1 1/4, you'll notice it's decreasing before 5/4, increasing after 5/4. Therefore, we have a local min at x equals 5/4. And that will conclude this lesson.